In this lecture, we're going to talk about how we use aerial photograph to create your 3D stereo models. How do we use aerial photograph to create ortho photos, DEMs, mosaics, etc. So just to give you an idea of what we're going to cover in this lecture, how do we use aerial photograph to retrieve data from such images. This is our table of contents. We'll be looking at the traditional method of creating a 3D stereo models, and it's called analytical triangulation. And then we're going to be looking at the more common or modern method using soft copy workstation to do the analytical triangulation. Then we're going to look at the low altitude mapping of your photograph. How do we use those images that were captured by aircrafts flying at low altitude. And lastly, we're going to look at digital ortho photos, which is a common product from your aerial photographs. Once aerial photographs are collected, they are required to be processed, and typically they are processed in a laboratory environment, which contains the necessary equipment and the programs in order to help in extracting the data from the aerial photograph. Let's look a bit more detail into what this involves. For each aerial photograph, there's a number of considerations. As you can see here, there's an example of an aerial photograph, and it's a vertical photograph, of course. And in some instances, we're going to have the effect of, depending upon the time in which a photograph was taken out, effects of shadows being shown up in the photograph, and shadows tend to obscure further details. So you want to be able to have a system in place that will help to minimize the effect of shadows. Also, you need to consider some photographs taken out by cameras that, because of the shutter speed being set at a specific time period upon which the photograph was taken out, you need to have proper exposure. And the aerial photographs tend to be a bit blurred if the shutter is open for long periods of time. Also, you need to consider aerial photographs are affected by crab angles. Remember a while ago we showed, in previous lecture we showed the effect of crab and of the aircraft. The pilot needs to keep the aircraft as vertical as possible. Also, in your vertical photograph you need to see your target. Alright, the target on the ground, which will have the ground control known at very high accuracy. Usually a licensed land surveyor will go out there and get coordinates of X, Y, and Z values of the targets on the ground. Also, the scan rate at which the photographs were taken out will also influence the type of aerial photograph. The format, is it a TIFF, JPEG? Also, that need to be considered, because some of the computer software that is written accepts only the common formats of the aerial photograph. And also, if you're using hard copies, what type of emulsion or film that was used, is it negative or positive? So each one of these considerations determines the usefulness of my aerial photographs. For the purpose of this lab, vertical photographs were taken out. So this is a vertical photograph as shown, and it's required to in order to create your 3D stereo model. In this section of the lecture, we're going to talk about the analytical triangulation, and this is the general concept of what is used in order to create a 3D model of the terrain using the aerial photographs. And the method is called analytical triangulation. Its approach is to use triangulation of target points. Other name for target points are control points, captured on your aerial photographs, and also use tie points that are shared between adjacent aerial photographs in order to compute the control points or ground control coordinates of the perspective center of the lens at the time each photograph was taken out in flight. So we're going to use ground control for our target points and identify tie points that are shared among the photographs in order to compute the coordinates of the perspective center each time the photograph was taken out. There are two methods in analytical triangulation: one, the traditional method, and two, a soft copy method. The traditional method is more manual, and we will go through a bit of the concepts behind it. And the soft copy method is the computer-based method of doing analytical triangulation. So let's look at the first one, your traditional analytical triangulation. As I said before, it's the manual method in doing analytical triangulation. You've seen in this slide before. I just wanted to show you again what is involved at the time the photographs were taken. Here we have the aircraft flying the area of interest. The terrain is at the bottom, and the aircraft is taking out a series of photographs. This is one run, and this is the other run that the aircraft is flying. So each one of these photograph and its conjugate. So another term used in photogrammetry, neighboring photographs are referred to as their conjugates. So each one of a pair of photograph and its conjugate would have a overlap area, and as you go from one run to the other run, you have a side lap area. Overlap area is 60% and side lap area usually 30%. Here is a cross-sectional view of what happens when the aircraft is flying the area. You've seen this also before. This is our photograph and its conjugate, and you can see the overlap extent and the entire area covered by each photograph. So the entire area is called coverage. The area with the overlapped section and its conjugate is called its end lap, or in other books they refer to it as overlap. And here you see a run or a strip. This is one set of photograph. This is one run, the second run, and we have a side lap, which I said before is 30%. Alright, and on this slide you see the aerial photograph in the background together with its control points. Those control points are visible on the photograph, and also on the ground we have the X, Y, and Z values for each of the points, which will be used in helping to create the stereo model. When everything comes together as planned, you get something like this, as shown in all of it's a collection of all of the photographs. And it is very important that the aerial photographs are collected based upon the client specification. Now, know that black numbers in the circles, they represent photo targets, as discussed before. This is an example of the many such examples of equipment used to generate or create our 3D model long ago. The instrument used had very basic principles. Shown in this diagram here is a mechanical bridging system instrument that has 3 projection systems. We have one here one in the middle and the other, where each one of these projection systems contained a diapositive. So we have one photograph, it's diapositive, and its conjugate is located here. So you can say first photograph, second photograph, third photograph, etc. And the second photograph and its conjugate. Now, using this equipment, they would have a light source, and the light source would project through the image in the diapositive, and a 3D model will be created using 3 of the photographs and their conjugates. On the table here, you would have your paper where the map will be traced out based upon where features are located on the 3D image. Here you have your measuring device, and it can be lowered or increase in height, and it's a representation of the Z component for each point that is plotted on the table. You can move this either in the X and Y direction, and it is representative of a mark that is used to trace out features from your model. The movement of each of these projection systems, if you look at them individually, they can be moved in the Y direction, or in the Z, or in the X direction, or in the Z direction. This is a linear movement. There is also rotational movement. Rotation around the X-axis is called omega. Rotation around the Y-axis is called phi. And rotation around the Z-axis is called kappa. Some books refer to them as different terminology. Long ago, rotation around the Z-axis was called a swing. Rotation around the Y-axis was called a tilt. Rotation around the X-axis was called an X-tilt. Alright? Rotation around the Y is called a Y-tilt. Just different terminology, but the same concept. Another set of equipment that can be used to create 3D models, rough 3D models, is what we call stereoscopes, and there are different types. Here you see a pocket stereoscope. Why is it called pocket stereoscope? It's because it's this pair of glasses can be folded up and be placed in your pocket, and it was typically used by the surveyors who, when they're out in the field, they need to create a rough idea of what the terrain would look like. They would use a pocket stereoscope and collect, and by using a photograph and its conjugate, we're able to see 3D, a rough model of the 3D area that they are in while out in the field. This is a mirror stereoscope, which is a more advanced stereoscope where you have more flexibility in moving the photographs such that when I take one and the other, there is no overlapping of the details. But with the mirrors, you can see both images using your eyes at the same time, and the brain is fooled to see 3D. So this is more for a lab environment. And here you see a more advanced stereoscope, which is similar to your mirror stereoscope, but it's much more intricate. We can have two viewing at the same time. So we have one looking through this eyepiece and the other looking through that eyepiece. Very useful, and this here is more expensive, and it's a lab, used in a lab environment. Now, as I said before, there are various types of stereoplotters. This is one stereoplotter that was used long ago. It's called the Kern DSR11 analytical plotter. All of these plotters have a optical system that the user can look through to look at the 3D model generated, and all of them will have a measuring device here that can move in X and Y direction, and there's a spin wheel at the base there to simulate the Z component of each point. As you can see here, there is a map being plotted on a computer model while the guy is looking through the eyepiece. Actually, he's looking at the 3D model at the same time. On this slide, you see a diagram of all the photographs taken out for a given study area or sample area as defined by the clients. But what I wanted to show you here is that in addition to the photographs, you would have on each photograph the control points that is on the ground. So we have a set of control points, first order control points, and also some secondary order control points. Note the location and how it's distributed throughout the entire study area. Ideally, you're going to want to have as much control points also within the entire study area. On this photograph, you can also separate them out. It can be first order, second order, it can be just control points that has vertical and also horizontal control. That is, horizontal being X and Y coordinates, and vertical control being your Z coordinate or your height above mean sea level. So in this case here, you have X and Y and Z, and X and Y and Z, but this here we only have the Z, the height above mean sea level at these points. This is a better distribution of control points, and there's a mix and match of all horizontal and vertical control, or whether or not it's just vertical, or whether it's just horizontal, or a mix of the two of them. Alright, so it's a good guide for the photogrammetrists to have when they're preparing their stereo model. This is also an output from the processing of the aerial photograph in terms of the control points, the residuals that the system would compute, and as a measure of the accuracy of the model generated. Alright, the more modern way of method of creating your stereo model is what we call the soft copy analytical triangulation method. Soft copy refers to the computer-driven application that does the processing of the images, and it takes into consideration the fieldwork control points that is used to create your stereo model. So let's look a bit more detail into what it involves. This is an example of a soft copy stereo plotter. It's computer with software together with 3D glasses. It's a big difference in terms of the traditional method using stereo plotters. Now in the soft copy approach, it follows the same procedure of orientation. You have to do your the three methods is your interior orientation, relative orientation, and then absolute orientation. Now in your interior orientation, what you have to do is identify where the fiducial marks are on the aerial photograph, and also put in the focal length of the camera, and also include also the coordinates of the principal point, the center of the photograph that you will get from your camera calibration report. All aerial cameras would have a camera calibration report. So together with your aerial photographs, the customer will also have to get a camera calibration report. Now, the system, once you put in all this information, the system would use the all of the information and compute a least squares adjustment and generate a RMS error, root mean square error, from which you could determine whether or not identifying your fiducial marks are within project specification. So that's the first step. First step called, just to reiterate, it's called the interior orientation. The second step is called relative orientation, where you have to remove what we call parallax. the X and Y parallax. It's what it involves is actually each object on your photograph has a certain amount of errors in terms of the X and Y location where they are in the photograph. What you have to do in the second step, which is our relative orientation, is select at least 6 points within the 60% overlap of a two photograph, that is a photograph and its conjugate, and remove the X and Y parallax at these 6 points. That, in a nutshell, is what we call relative orientation. The third step is called absolute orientation. It involves using the fieldwork coordinates that the surveyors would collect out in the field using X, Y, and Z values, and inputting that into the model such that you introduce real-world coordinates based upon a coordinate system. All right, and it involves, again, going through similar procedures that you would have done in relative orientation step. I have given a very extensive description what soft copy approach involves in the lecture notes. Please read it through, and very informative, and of course consider this as material for further compounding upon your knowledge in this area. Let's look a bit more detail into the various types of equipment that was available long ago that is used to collect or create a 3D models, stereo models, using the traditional method. Now, please note that the traditional method requires much more preparation, and it takes a longer time to achieve what you want to achieve in terms of creating a 3D stereo model at the level of accuracy that is required. This includes the manual setting up of your diapositive onto the projection system of all of the instruments. They do have a common name of the traditional instruments, which we call stereo plotters, and there are two general types. One being what we refer to as mechanical stereo plotter, and the other the optical stereo plotter. Mechanical stereo plotter makes use of light rays, and these light rays are represented by a pair of metal rods on the instrument. In the optical stereo plotter, the light rays are represented by a pair of rays of light. So for every point on that photograph is defined by one light ray per photograph. Alright, so for each point there are two light rays, one from each photograph and its conjugate. They both require human input of data in order to create a 3D model. That is, mechanical and optical require input from the camera calibration report, and the other input in terms of the 6 points in order to remove the parallax and the relative orientation procedure, etc. And as such, because there's so much human interaction, there is also the possibility of introducing errors into the entire procedure. As compared to your present day computer generated 3D models, it is controlled by least squares adjustment, which is programmed into the software. Using the traditional method, other preparations need consideration, such as locating where the control targets are, checking to see that the target numbers are correct, and other considerations. So let's look a bit more of the different types of stereo plotters. In this example, you see a second order stereo plotter, and for simplicity, they all contain common features. For example, here you have this is a mechanical stereo plotter because you see the space rods, and I said before, for each point in your stereo model, every single point is defined by two rays of light. In this case here, those rays of light are indicated by the space rod. This is your mouse that can move in the X and Y direction, and there's a little wheel that will move, you can rotate to represent the Z direction. In this machine, you will have as you can see, a table where as you look through this optical piece that views the images, first image and its conjugate, you would see the 3D model in that eyepiece, and as you move the mouse on the table, it's actually integrated with this drawing table. Anywhere you move that mouse, this pen draws the feature. This is a third order stereo plotter, and it's a mechanical stereo plotter. Why? Because you see the space rods again. The photographs are held in these trays, and there is a table that the map will be placed, and here you have your Z wheel, and this mouse can be moved in the X and Y direction. So similar configuration, and the results is as good as the accuracy of the equipment. So this is a third order stereo plotter. This is another third order stereo plotter, older type version of the stereo plotter. It's a mechanical stereo plotter. Why? Space rods, as you can see. You are directly drawing the map, which is placed at the base of the equipment, and you will be viewing through special glasses. Your photographs will be held in one tray and the other, and it's conjugate at that location there. Very outdated. This is the general concept of the stereo plotters, in particular the mechanical stereo plotter. We have the rods, and the rods in them are connected to a tie rod that is actually looking or pointing to certain features. As you move this mouse tracing stand in the X and Y direction, so too is that tie rod indicating where you are looking at on a diapositive. Now the diapositive it is held in a tray and has a proper registration mark that is registered through the fiducial marks on the photograph. The stereo plotters typically would have light that will shine through the diapositive and fed through the optics, and using binocular viewers connected to the stereo plotter, the user would be able to see the stereo model in a 3D environment. This is a representation of the stereo model. The same concept for the other diapositive. This is one photograph and this conjugate held in a tray, and the same concept, being able to view the same point on your terrain or your stereo model and be able to measure off or trace out the feature that you are seeing or measuring on the 3D stereo model, which is traced on the reference table that has the paper where a pen is connected to a tracing stand. So the concept is the same in all of the stereo plotter. Floating mark is a concept used just like your mouse, where I can put the point of interest that I want to capture the X, Y, and Z location. What is that coordinate at that point? So on the photograph you have point A, B, and C, the floating mark. If I want to measure where these features, or if I want to measure the coordinates at point A, B, and C, I would put the floating mark at points A and measure, and then point B and measure it off, and C and measure it off. When I say measure, I mean you would digitize where these points are. Once you digitize it, you will be drawing that directly onto the map that is connected to your model, and it's actually, there's a pencil on the tracing on the measuring device where features are traced onto the map. This is a first order analytical plotter. It's a very old one. It's connected to a computer. Remember, the analytical plotters, the processing is done using software or program, but some of the physical components of your stereo plotters are still visible. For example, this is your X wheel and your Y wheel. So in order to move, there is no mouse on a table. You would have to turn these and move it in the X direction, and turn these into Y direction. And this little wheel at the bottom is your Z wheel. It is the, if you want to move your floater mark, either positive Z or negative Z. This is a smaller version, a better version, modern type at that time. Connected to the computer again, and it's smaller compared to the previous slide, but the concept is still the same. You have the X and the Y wheel, you have your computer, the optics, you have your diapositive here and diapositive here, you have your Z wheel. Concept is still the same. Now, this is an example of the end product in the modern type soft copy workstation, where you will have the imagery in the background, and this imagery is a 3D image, of course it's a stereo model, and overlaid onto that, as you start drawing out features, you are drawing these features that is interfaced with some CAD package, for example AutoCAD. You see different colors of these lines. It means that they are on different layers in AutoCAD. So it's very useful to start drawing features not only on a single piece of paper, but also you can start separating all the features into different layers when you work with digital data. So in AutoCAD you'll have the roads on one layer, then you have the buildings on another layer, for the main reason that you're going to use this data for other applications to do, you know, whatever you want to do with the data. You can also, once you have this data, for example spot heights I would collect from this stereo model, I can create a 10 triangular irregular network, which we would have discussed in your GIS sometime when you were going through the course. Once you have height information, X and Y location of set of points, especially in areas where there's sudden changes in the terrain, a set of irregular triangles that take into consideration the heights of these points, and it is based upon this terrain is being generated, which we later converted into what we call a digital elevation model, which is a common term, DEM. Now let's talk a bit about the soft copy workstation, how data is collected using the soft copy workstation. And this came out as part of the approach of doing everything, or doing applications using computers, where we try to automate data collection from aerial photographs using the computer, because our aerial photograph can be scanned in, and once it becomes digital data, then whatever we do on a manual basis using the traditional stereo plotters, we found a way of doing the same thing using the computers once the aerial images are in digital format. The first thing one may think is that why we do not scan the aerial photograph and do the same thing. Well, that is done, and this is done using soft copy workstation. This is an example of a soft copy workstation. As you can see here, you have two monitors. One monitor would have the graphic component, the other monitor will have the 3D image, and in order to see the 3D image you would typically have to wear some 3D glasses. Connected onto these computers you have your CPU, of course, and through your CPU you would connect to the peripheral, which is the images in this little compartment here. Those images are scanned in, or if it was originally collected as digital data, then it's already stored in the hard drive. This is an example of a soft copy stereo plotter. The brand is Leica, and there are various brands out there, but they still follow the same underlying concepts. You've seen this slide before, but as I mentioned before, once you have your 3D model, you put on special glasses, and you will be able to see the 3D image. You will have a mouse that controls what you're seeing here at the bottom. It's the mouse that the operator can make measurements or digitize the features that you would see on the 3D image. That is stored in a CAD file. There are various pros and cons in terms of the soft copy workstation product. There are also, one of the main benefit of this is that you can do heads-up digitizing. You could also do, it's good for updates, and it's faster setup in terms of setting up the 3D model when compared to the traditional method. It's more accurate because what the system does, it does least squares adjustment when you're registering each photograph by way of the fiducial marks, location, and also takes in consideration standard deviation of control points, and it does least squares adjustment for every point that you would capture. It's more accurate, and as such is a more accurate 3D model generation. And of course, another good benefit of this is that the data is already in digital format. You can use this in any other application, export it in whatever format you want. An example of a common low altitude mapping photography software is called LAMP. There are various applications of them. It's applied in highway design, roadway crack study, in terms of if there are cracks on the roadway. I want to use a LAMP to be able to do some analysis on it. Looking at also taxiway ramps and runaways. LAMP is a common method or procedure or software used in looking at low altitude, meaning the aircraft is flying at very low altitude, mapping areas, and it's very accurate. This is a test project done using LAMP, and what you're seeing here is imagery, overlapping imagery of from the LAMP project done in 1996. Note here the details are very well defined. You can actually see the markings in the road, the cars on the road, and also included in this test project is control points that are visible at that altitude. It's a low altitude. Alright, and in this test project they wanted to use existing controls and be able to derive a cross section as shown along the as shown by the red line. So what was done is that yes, they needed more control points in order to get a good representation in terms of the stereo model. So what they did is went out in the field with GPS receivers and get controls, more additional controls that are visible on the ground. On the photograph, and using those control points, it was included into the project, the LAMP software, and now they're able to get a better representation of the stereo model. Here you are seeing targets being placed outside the traffic lanes on the roadway. And why do we use LAMP? It's number one reason is it's safety reasons. You have the ability here to capture images at a low level and at a very high accuracy in terms of the details that you are picking up in an area where it's always being used by some motorists. So even though it's very dangerous to have people out on the edges of the roads on the shoulder, motorists will be properly warned of what's going on and to drive with caution. What you're seeing here is flags being used to warn motorists of people on the shoulders of the freeway, and what they're actually doing is painting on the ground control points so that when the aircraft flies the area, they can pick it up on the imagery, and following which control the X, Y, and Z values of these control points at the air and the shoulder will be surveyed using GPS. On this slide, you can see some of the targets being placed. It can be a form of a temporary target instead of it being painted permanently on the ground. And so this is going to be at a level of detail that the aircraft will be able to pick up. Here you see the output from LAMP, and it's doing a crack analysis. It's a CAD environment, of course digital data, and the CAD data set, they were able to actually capture the cracks on the road. Being a 3D stereo model, they were able to digitize where these cracks are on the pavement. Very useful information. But note also you have the ability to get the details along the shoulders of the road and outside and the area beyond the shoulders of the road. On this slide you are seeing a LAMP data set. It's the imagery, and also together with the imagery, if you have the ability to zoom in, you will see the control points also showing up on the imagery. From this LAMP data set, the data extracted is shown at the bottom. 1 inch is equal to 30 feet, and what you are seeing here is a triangular, that irregular network of points of the roadway at the intersection of 10, which is used later on to create a 3D model. Very useful. Note here that a lot of details is picked up along the road together with areas along the road reserve. On this slide you see a zoomed in version into the collected data, and more detailed look at the data captured along the roadway and its reserve. You can actually see the irregular triangles based upon the points captured from the stereo model generated from LAMP. Very useful information, very accurate. What does it take to make a delivery to the client from a Photogrammetry software? It involves a lot of post-processing of the data, and once you do the post-processing, you would typically have a 3D model that the client can view and make measurements. In this section we're going to look at how do we edit the digital data. Now sometimes you can create your 3D model, and together with the 3D model package it a software, a viewer, which can be used to view the 3D model. It doesn't mean that the client it does not mean that the client have to have a full-fledged 3D software, which is very expensive software and also hardware. So the product can be the 3D model together with a viewer. Usually the viewer is not really an end product to the client, but if the client needs to look at the data, then a viewer is is usually included. The data is expected, the final output from your 3D model is typically a CAD format. Some CAD package like AutoCAD, which stores its data in the format of a DWG file format, or some of them typically would have a MicroStation software which has a DGN format, and there are other formats like DXF. So in this section, let's look a bit of some examples of how the data from the stereo model is edited. Now, because the data is being stored in a CAD file, typically CAD file have multiple layers. So what you're seeing here is that each one of these numbers represent a layer in which information is stored. So for example, we have layer 46, which is a set of lines, and the type of lines is solid, and the number for that particular line is 1, and the information is stored per layer in each DWG file. So all CAD packages would have layers of information. This is an example of a MicroStation CAD file in which all of the layers for that particular area are turned on, and the information is displayed in different colors. You can choose whatever color you want to display. Here you have the road edges in white, and then the vegetation in green, and all the other information. You have contour lines that are in light brown. The text also can show up, in this case it's blue, etc. So all of the information are stored separately on separate layers for the main reason that the data can be further processed in other software. Zoom in into this area here. If we zoom in to get more detailed information using the same CAD file, this is what we get using MicroStation again. The same area and much more information is being displayed. Here you have a pedestrian crossway along this filter lane. You have vegetation, and you have the road edges, and also if you have the information that is under the road area, you can also include that in your CAD file. Much more detailed information, because that is the level of detail the data was collected. Here you see the 3D view in MicroStation. You can create a 3D model of the same data once you have the necessary height information for the points captured, so you can switch between 2D and 3D. What does it take to make a delivery to the client from the Photogrammetry software? One form, another form in which the data is delivered is in the form of a digital orthophoto. Common terminology being used, and what it involves: an orthophoto, also called in some books an orthophotograph. It's an aerial image that has been geometrically corrected. Some books refer to them as ortho-rectified, so that the image is uniform from edge to edge. As you move, as you collect the data on the aerial photograph at the time it's taken out by the frame camera, the error increases as you move from the center of the photograph. So as you move outwards from the center of the photograph, due to the errors of relief and tilt and lens distortion in the camera, the images on as recorded on the aerial photograph would have inherent in it some errors due to the errors of relief and tilt and lens distortion. Ortho photographs are commonly used in the creation of a geographic information system application. Software can display ortho photos and allow the operators to digitize and place line work text annotations and do on-screen digitizing, because the orthophoto typically would have the errors of tilt and relief and lens distortion minimized, and also inherent in it, it will have a coordinate system. Okay, so as the operator digitize the features that they would see on the orthophoto, they will be collecting 2D data based upon the image displayed. This is a diagram of what is relief displacement. Relief displacement is because of the area being captured, especially in mountainous areas, the top of mountains will be recorded first. So at this point A here, it will be recorded on the film first, then B as located here. B has a further distance. That ray of light that is reflected at the point B will take a longer time, and it will be recorded last in relative to point A. Now point A would be recorded once it goes through the camera lens, will be recorded at a distance closer to the center of the photograph, which is an error. Okay, in actual fact, the X and Y location of point A should be as if it's a capital A prime, which is supposed to be at this point here. So because of the X and Y location of where A is located on top of the mountain, it should be that when at the time of the photograph is taken out, it should have been where the as if the point A is actually at this location, capital A prime, which is on my image A prime. So that's the actual, that's the correct location of where the top of the mountain, the correct location in the X and Y coordinates. But because the point capital A is on top of the mountain, it reaches first compared to B. But because this A is at top of the mountain, it's actually stored at this location, A double prime, which is an error in terms of its X and Y location because of the relief. So that's relief displacement. In some books they refer to it as relief displacement. This is an example of the images on a photograph as displayed on the original photograph that contains the effect of relief. You will notice the buildings tend to lean as they move away from the center of the photograph. The building appear to lean, and there's a displacement from the center of the frame. So as you move away from the central location, the building seems to be, actually matches up where it's supposed to be on the ground. But as you move away, like for example this building here, it's leaning backward. Okay, it appears to be leaning. Similarly here. But when you digitize or capture the X and Y location of buildings, you typically want to get its X, Y on the ground. But because those buildings are high rise, they appear to be leaning as you move away from the center of the photograph. So this is the effect of orthophotos. A more pronounced example. This is an example here where you have an overpass with an underpass. Let's zoom into this area here and you'll see the effect of it. Alright, now here you see the overpass is actually being digitized incorrectly. Alright, in actual fact, the overpass should be where the red marks are located. But because the overpass is at a higher level than the underpass, if you are to take the image as is and digitize as seen here, your overpass will be at an incorrect location in terms of an X and Y location. In actual fact, the overpass should have been in a properly digitized, such that in this case here you have the overpass seem to be way above where it's supposed to be. Here, this is what it should be in its correct location in terms of the X and Y location of where the overpass is. So this is obviously, it's an ortho-rectified image in which the height of the overpass is actually removed, and it appears that the overpass is actually on the same height of the underpass. And in terms of the actual digitizing of the features, in terms of its X and Y coordinates, it is accurate, better than the original image because of the relief is removed. Here you see another example of relief error. This is the original aerial photograph, an area in Vancouver. We have here the road is actually shows up because of the undulating terrain. It shows up as if it's a corner, but in actual fact, when this image is also rectified, the road is a straight line road from this point till down here. So even though it looks like there are corners, because of the terrain, it's actually going up the edge of the side of the mountain and comes back down, and then it curves slightly here. When it's auto rectified, it's one straight road. Another example here of an ortho-rectified image where all of the images in this set of aerial photograph, there are some inherent errors due to the relief, and when all of them are applied in creating an ortho-rectified seamless image of the entire area, when we compare the original aerial photographs with the ortho-rectified photograph, you can see some obvious changes is being displayed in terms of the location of the features. So here we see a continuity of the road or the river, and you can see how the pixels are actually resampled in order to address the effect of relief. This is once you have an auto-rectified photo or a set of auto-rectified photograph, because they have the coordinate system built into the auto-rectified photographs, and also the effect of relief, you can use that and drape that image over an existing 3D model like a digital elevation model to create a realistic look of the terrain, of the 3D terrain from your DEM. Alright, this concludes our discussion on this section, looking at lab development. As I said in previous lectures, download the PowerPoint notes, go over the material, go over the PowerPoint presentation, and we'll continue with the next lecture.